So we'll be talking about multi-stage fluvial channels as a resilient flood mitigation solution. And if you're not familiar with all those terms, don't worry, 30 minutes from now, you'll be well-versed in the terminology. So a quick overview of our presentation topics today. I'll introduce the learning objectives and our presenters. We'll give a quick synopsis of some results coming out of the Nueces Regional Flood Plan and how multi-stage fluvial channels could be incorporated into some of the flood mitigation projects. We'll talk about the relationship between sediment and water, give a brief overview of what a nature-based solution is and what a multi-stage fluvial channel is and its benefits, and then we'll wrap it up with some takeaways and questions. So before we get started with the details of multi-stage fluvial channels, we wanted to go over the learning objectives for our presentation. So the takeaway points that we want everyone to go home with. First is, how are sediment transport and flood mitigation related? Now I know the sentence starts with the word how, but it's really a why question. Why are we even concerned about or considering sediment transport when we design mitigation projects? Second, we want to answer the how question. How do we incorporate sediment management into a flood mitigation design? And the third objective really answers the what question. What is the importance of considering a multi-stage fluvial channel in our design? And what are the benefits to the community when we consider these factors? So now that we've gone over the purpose of the presentation, let me introduce the presenters for today. So for those of you who don't know me, my name is Sarah West, and I'm a project manager and professional engineer with Fries & Nichols here in the Corpus Christi office. I've been working in the Coastal Bend area for over 20 years, and although I've worked on many different types of civil projects over the years, my main area of interest and focus has always been stormwater. One of my most recent projects was the first cycle of regional flood planning, which I know you've heard a lot about today, where I was the Coastal Counties lead for the Region 13 Nueces Regional Flood Plan. With me today is George Fowler, who is Fries & Nichols' expert on the topic of multi-stage fluvial channels. George works out of the Austin office and has 15 years of experience in flood mitigation and geomorphology. He's currently working on the Texas Water Development Board's Nature-Based Solutions Flood Mitigation Manual and leads stream restoration projects throughout Texas and other parts of the country. Fries & Nichols, just a little bit about our firm, is a multidisciplinary firm that with offices throughout the United States, but we started out in Texas, and we're actually celebrating our 130th anniversary this year, so we've been around for a little while. We have been providing services to the Coastal Bend area for almost 100 years. Our first project was laying outfall sewer into Corpus Christi Bay back in 1926. And components of this system that were designed by Fries & Nichols founders are still operational and lie within the historic Broadway Street right-of-way. So George and I are excited to be here at the Nueces Basin Summit because it provides an opportunity for us to share with project sponsors ways to avoid unwanted outcomes after a flood mitigation solution is built. For example, when sedimentation occurs in an undesirable location within a channel, it can lead to perpetual maintenance needs and recurring costs to clear the sediment. With the recent completion of the first cycle of the Nueces Regional Flood Plan and the second cycle poised to kick off later this year, it gives us an opportunity to look at proposed projects in this region and to identify opportunities to look at multi-stage fluvial channels as potential solutions. So a few stats from the first cycle of the Nueces Regional Flood Plan. There were a total of 31 flood mitigation projects listed in the Region 13 plan. 10 of those FMPs were projects that modified a channel, and 20 FMPs included some form of discharge reduction. So these solutions can result in perpetual maintenance if appropriate strategies aren't employed during design to consider sediment management. So let's take a look at a few different categories of flood mitigation solutions and how modifications to the system when a project is implemented can affect sedimentation and erosion in a channel. So just a quick note as we get started with some examples. Although we pulled these examples from the Nueces Regional Flood Plan, these are meant to be representative of similar types of projects, not because we have studied these particular projects in any detail at this point. We aren't providing results from a study of these projects, and these are just meant for discussion purposes of what could happen and what to look for during design. So this first example is of a low water crossing that is going to be improved. The roadway surface will be raised and culverts or a bridge installed under the roadway to pass the stormwater. The intent is to reduce roadway flooding and improve the level of service of the crossing. When you have a wider cross-sectional area of channel approaching a roadway crossing, it narrows down to pass through the culverts or a bridge. So we have impacted the hydraulics of the system. If you increase the cross-sectional area of a crossing, it often reduces velocities and shear stresses in the channel, and that's where you can have a change to the relationship between flooding and sediment transport. Our second example is a project where modifications to the channel itself are occurring. The proposed improvements are to widen the channel, thus reducing the extents of the floodplain and removing 74 structures from the floodplain. When you widen the channel, that increases the cross-sectional area and lowers the water surface elevation. And when that happens, the velocity slows down and shear stresses get lower. Shear stress is the physical property of water that is responsible for moving the sediment, whether along the channel bottom or within the water column itself. So when the velocity and shear stress are reduced, that will lead to deposition of that sediment. That isn't necessarily a bad thing because rivers tend to pick up and deposit sediment in a balance, but where it becomes problematic is where that balance is interrupted. And we start getting buildup of sediment over time, particularly if that buildup occurs in an undesirable location. So if we get buildup of sediment, that then actually reduces the cross-sectional area of our design, and now our design, which assumed a wide cross-sectional area to achieve flood mitigation benefits, has also been reduced. So now our flood mitigation benefits are not being achieved as designed. Our third example is of a hydrologic change due to a proposed project. So we have two things going on in this example that will impact not only the peak flow of water, but also the volume of water. In this example, there is a detention pond proposed, which will likely reduce the peak flow along the channel. So that is a change to how much water and how fast it is moving through the system. And then there is also a diversion of flow from one system to another, which changes the total volume of flow going through both of these systems. So a change in how much water goes down our system over a period of time. When we reduce the maximum peak discharge or reduce the volume of water in a system, then we now have less fast-moving water going through the system, and that might result in sediment no longer being carried or moved by the water and could potentially end up increasing the amount of sediments that are deposited. So to recap, these general categories of change, hydraulic and hydrologic changes, often result in impacts to the sediment transport and flooding relationship of a drainage system and should be evaluated as part of a flood mitigation design. And now I'm going to turn it over to George, and he will discuss how to actually do these evaluations.
Thank you, Sarah. I'm going to try to walk around because I'm a little cold and just had some lunch. So I need to wake up a little bit. And everyone out there too is probably, their blood is leaving your brain and going into your stomach to help digest that great food that we were served today. So I'm going to try to pick up our vital signs by talking about a couple things that make us perk up when our hearts start to race and our blood pressure goes up, and that's stress and money. And if we don't consider sediment management when our flood mitigation designs are being developed, we could end up having perpetual maintenance removing that sediment. And what does perpetual maintenance look like? That means getting in, excavating out the sediment that's filled up our culverts, filled up our rivers, and also our flood conveyance channels. And what that is? That's more money to remove that sediment, less time to do other things, and a heavier headache when people call us up and say, hey, why is our design filling with sediment? Now we have to go out and fix it again. So what I'm going to try to do with the rest of this presentation is to leave some wisdom with you all, because I know half the audience is about potential project sponsors, and the other half is maybe some design consultants. And what I want to do is just leave wisdom for you all is if you're a project sponsor, ask your design professionals questions. Have they considered sediment management when they develop their flood mitigation designs? And for the design professionals out there, consider flood transport in your flood mitigation designs, because we want our projects for our clients to work in an order that we don't have any unwanted consequences when it comes to sediment deposition. So as I walk through the rest of the presentation, I'm going to leave some things for you to take back with you to be able to ask these questions to your design consultants, and then to further when you go into final design. And why we're talking about it today is that we're having opportunities that we have we have projects now that are probably going to get funded through FIF, and now they're going to go into final design and construction. And this is an opportune time to have these conversations about the relationship between sediment management and flood mitigation design. So it was once said that streams are the gutters down which flow the ruins of the continents. This was said by what many people consider the godfather of geomorphology, which is the science between rivers and streams and their surrounding landscape. So Luna was like the Stephen Hawking's of astrophysics, or James Brown to funk music, or Sam Houston to present-day Texas. So he's a godfather of this science. And what he noticed back when he started getting into this field is that rivers have a stable plan form. They have a stable shape when they're in balance with their sediment transport and the floodwaters that go down it. The channel shape has some very key indicators within its shape. One of those is called the bankfill stage, which is the point of inflection between the low flow channel, where water usually goes in any average day, and a relatively flat stage. So as floodwaters come through, they spill out onto this bankfill stage. So now the energy that's in that rushing water is dissipated on that relatively flat feature, but the moving water in the low flow channel can still continue to carry sediment through the system. As we start having higher and larger flood events, there's another point of inflection called the flood stage, where it's another bench where floodwaters will spill out again into a relatively flat stage, again dissipating the energy, but still allowing water in that low flow channel to move and carry the sediment through. Other things that Luna noticed that rivers have features called point bars, which are areas where sediment will deposit, but then be transported over time. They're constantly being reworked. And why that was important is that then the sediment is always in balance with its flood moving through there. So the shape of the channel may change over time, but it's going to be relatively similar to if it's in stable plan form with its sediment transport. Now that's been studied in the field. It's also been studied in flume settings, where the rivers have a natural plan form where they have meanders. And in this exhibit here, the meander is that little curve that you see that goes around the bend, and inside of that is a floodplain. As the water goes up in the flume, water will spill onto that floodplain, dissipating the energy, but that low flow channel where the red arrow is going around the curve still has enough force to move water and carry the sediment through without depositing. And so all of this scientific and engineering understanding allows us to predict what the response is going to be in our flood mitigation designs if we change it either from the hydraulics that Sarah talked about earlier or the hydrology. And so now we have an understanding of what our response is going to be so we can make informed flood mitigation designs. Now, this conceptual model is another fundamental principle of geomorphology. It's called Lane's balance. It's a simple cartoon scale. And how it works is this. If the scale on the right side goes down, so the side with the cup in it, for example, if we add more discharge, more water into that cup, the scale on the right side will go down. The black arrow in the middle will then swing to the left into the erosion side. Erosion is when the stream has more power than the ability of the stream to resist that power for erosion. And the converse is also true. If we remove water out of that cup, then the scale starts to go up. And then the black arrow in the middle swings into sedimentation. We see this phenomenon very, very evidently in our watersheds. Think of an example where you might get more discharge into our receiving waters. An example of that is urbanization in our watershed. We put a more impervious cover on, less water, rainwater is able to infiltrate in our soils, it runs off into our receiving waters. We put more water in that cup, the scale goes down, and that black arrow in the middle swings over to erosion. Who has noticed in urbanized watersheds that aren't mitigating their peak discharge is your receiving waters are beat up. They have a lot of steep eroding banks, a lot of failed trees are falling in there. That's an example of this Lane's balance that's not in balance. The other way that this scale can work is if the pan that that cup is sitting on can shift to the left or to the right. Sarah mentioned earlier about increasing the cross-sectional area to convey more floodwater through. When we do that, the cross-sectional area increases, but the continuity equation, discharge equals velocity times area, mandates that the velocities have to go down. So the slope on the top of that bar there is actually the energy grade line slope, which has velocity as a hydraulic component in it. And so if we reduce that velocity, our slope flattens. We move that pan with a cup of water towards the center of the scale, we have flattened our slope. Now that scale then tips and our black arrow goes into sedimentation. So we can see that in many examples out in the field and also in our labs. So let's apply that scale here. Let's apply that example, this conceptual model. Here we have a low water crossing, low level of service, completely inundation happens frequently. What do? Common area, increase the cross-section area, put larger culverts in, raise the profile, adjust the cross-section of the encroaching stream. We have now been able to achieve and push our water through that low water crossing. Well, we increase the cross-sectional area. Our velocities go down. That slope flattens, and now that scale tips into sedimentation. And time again, when we open up our areas, we now have sediment filling into our culverts or into our streams. And so what does that do? Now we don't have that conveyance that we planned for, that we designed for to achieve our flood mitigation benefits, because it's obstructed by sediment. Now we have to go in and remove that sediment. More time we have to spend getting in there, more money we have to time to get in there, less time for other things, and more heavier headache because our design isn't functioning as what we intended. And that sedimentation can happen relatively quickly in one single flood event or over a period of time. Now here's one design consideration that you can ask your design professionals. Have they considered sediment management within their flood mitigation design? And for your design professionals in the room, here are some simple things you could do to see if I have enough sediment volume upstream of the flood mitigation project that could cause these unwanted results. And what I'm trying to do here is give some ideas about approaches to do that doesn't cost really a lot of additional money or unique exploration of investigations to be able to solve these things. There are also some common tools. I will talk about something a little unique here. But basically, you can answer this question, do I have enough sediment volume upstream, is by looking at some LIDAR comparisons, taking an old LIDAR data set, putting a newer one on top of it, and looking for areas of change where the landscape is missing in the newer LIDAR data set that's been caused by erosion. You can quantify that volume of landscape loss and answer that question if we have a lot of sediment coming down into our flood results. USGS stream gauge data is also another source of data to understand how much volume of sediment are moving through. People like going out in the field, getting out behind their computers, and go out and look. Can you measure eroding banks? Can you see erosion happening in our watershed upstream of our project area? If you do, there are some standard forms and investigations you can do. The first one's called the Bank Erosion Hazard Index, or BHI for short, which measures the geotechnical stability of the eroding bank and its acceptability to erosion, which you can turn into an erosion rate and get a volume from. So there's other field investigations to do. I'd like to make a plug for this root dendrogeomorphology investigation, which is a cutting edge science, and that's a pun intended, because you go out and you actually cut into a tree root, an exposed tree root, and the difference in the anatomical structure of that tree root tells you how long that erosion process has been going on. And then from that, you can determine the amount of volume of sediment moving through the system. So these are just some things to ask design professionals as you're moving forward in final design. Have we considered sediment in our flood mitigation design? Now we'll talk a little bit about nature-based solutions. NBS, you've heard that term kicked around a lot, but one giant step back about nature-based solutions conversations is an umbrella concept and covers everything from bioretention ponds to carbon sequestration. But what I want to focus a little bit on the FEMA definition is the part about natural features or processes. Now, the multi-stage fluvial channel that I'll talk about here in a second is a natural process. It emulates Mother Nature's intent of being in balance with rivers and their sediment. And so by designing a multi-stage fluvial channel, we are emulating that natural process of the balance between sediment and flooding. And in light with a trip with nature-based solutions, we've heard this before in a previous presentation, the terminology of triple bottom line. Now, triple bottom line for a nature-based solution is trying to accomplish multiple benefits from usually traditionally not associated elements, such as the environment, and also the social elements. So in the environment, trying to diversify, provide ecological uplift within our solution. Social, we've talked a little bit earlier today about how the impacts of flooding has on society, mental well-being, et cetera. And the science is starting to show that people, if they're more connected with nature, they're generally happier, less prone to disease, mental health, et cetera. And then the economics. The greener things are, the more valuable they are, especially in urban environments. And also providing recreational opportunities does provide economic benefit. So a multi-stage fluvial channel is a nature-based solution because it emulates that natural process of sediment transport and flooding. It emulates the balance between the two. And so the goal of the multi-stage fluvial channel is to recreate a channel shape that allows the sediment to pass through while achieving our flood mitigation benefits. So by doing that, we have now built in resiliency into our design. We have accounted for the other part of that, besides the floodwaters that go through, the sediment that comes through. So we've designed for that sediment going through, and we have built resiliency within our channel. Here is an example of applying a multi-stage fluvial channel. This is a rendering of a stream that you've probably seen something like this before, where it's currently eroding. The banks are near vertical, we have trees falling in there, and we also have a flooding problem. We have floodwaters into surrounding homes. This is an example of where lanes balance is not balanced, where the erosion potential in the stream, that shear stress we've talked about previously, is now in the erosion. So the scale has gone down on the right side, moving that black arrow over way to the left. So what we want to do is compensate that. So with our discharge filling up into our cup, the scale on the right side has gone down, and that black arrow has swung over to the left. Now, to counteract that, we will now build in our multi-stage fluvial channel, which then wants to shift that pan closer to that center of the scale to pull that black arrow towards the middle. So now what we have done is that we have redesigned our channel. We have a low flow channel that the sediment will continue to move through. We have a lower stage bench, that bankful bench, and then we have an upper stage floodplain bench. Now, this is where the other parts of the nature-based solution benefits come in. The environmental benefit. We can now plant different flora at the elevations, because some flora like their feet wet more often. Others are more terrestrial, higher up, a more mature tree canopy. We can now incorporate the social element, bring our community members into our stream corridors via recreational paths or other opportunities for them to engage in nature. And we can also, there's a big economic driver for that too. More people coming to our communities to participate in nature, the more desired they come here, they spend money in the towns. And then also putting some rain gardens up on the higher floodplain benches as another opportunity to improve water quality. So we have now designed our multi-stage fluvial channel. We have flattened that energy grade line slope and brought our channel back into balance. So you've heard a lot about flooding and flood mitigation, modeling, flood mitigation solutions analysis, alternatives analysis. So I wanted to just take this opportunity for everyone to realize that this is the opportune time to start incorporating sediment transport in these flood mitigation solutions. Because all the modeling you've heard today assumes one thing. Well, there's a couple assumptions, but the big thing for sediment is one, is that the boundary of the shape of the channel does not change over time. It does not account for sediment building up in your channel. It assumes that that channel is clear and that boundary, that geometry across a cross-section or in a two-dimensional model doesn't change over time. And if that assumption is broken, then our flood mitigation designs are not going to be achieving the benefit that we are claiming they are. So this is why it's very important when you start doing a drainage master plan or a flood study, that when we come to the alternative analysis, please incorporate sediment management, because if not, then in order to make our flood mitigation goals, we're going to have to maintain and remove that sediment. So as this is an example up in Pflugerville, just north of Austin, where we have a couple structures in the floodplain, some bridges are overtopped really frequently, and in the drainage master plan, the decision was, well, let's just cut out a big part of the floodplain, make a bigger, wider channel, throw our flood waters through there, and then we pull our structures and our bridges out of the floodplain. Well, they achieved their flood mitigation goal, but they assumed that the area where that proposed ground is doesn't change. It doesn't get filled in with sediment over time. And what happens when that fills in over time, now our assumptions of a free flowing channel have now been broken. Now we have to go in and maintain that. That's where we have to spend more money. We have less time for other things. And we have people questioning our ability to design something that's actually resilient. So that sediment can fall out in just a single flood event, as we saw in some places in Harvey and other areas, or it'll just build up over time. So if we flatten that slope by opening up that cross section, we are making ourselves more prone to sedimentation, because that scale is now sliding into that sedimentation part, and now we have to deal with ongoing maintenance. So I put together this really quick model, hydraulic model, just as to put some numbers to this. And this is part of when the design professionals are looking at flood mitigation solutions, they'll use this. So the tools are already there when you're in the preliminary stages or the final design stages, to incorporate sediment management into your designs. So here's a simple one-dimensional steady state HEC-RAS model. There's a house here in the black polygon, and then it's being inundated at the 100-year and the 25-year flood event. So our flood mitigation goals is to keep the 25-year, which is the second line from the top within the channel, and then lower the highest line on the image by the black polygon below the first floor elevation of that house. So the first thing we do is open up the channel, make a big wide channel, drop in, which drops the water surface elevations, and we have achieved our flood mitigation goals. But wait, the bar graph on the right shows what happens when we open up the cross-sectional area and reduce velocities. Under existing conditions, the red bars show what the shear stress value is, and that's in the units of pounds per square foot. Shear stress is the hydraulic constituent that forces sediment through the system, either along the bottom of the channel or keeps it suspended in the water column. You can see what the existing shear stresses are at the different return interval floods under existing conditions in red versus what it is in blue. And it's a great reduction in shear stress. So those numbers tell us that, wait, we should really be considering about sediment, because our clear channel now is going to start to fill in because we have reduced the shear stress so much under proposed conditions that we're going to have to probably go out and maintain that channel. Now, with a multi-stage fluvial channel design, we incorporate the flood benches, the bank full bench, which is that first little notch you see on the low flow channel, and then the higher floodplain bench. And so now our flood mitigations are still being accomplished. 25 years within the channel, 100-year water surface elevation is below the first floor elevation of the house. But our shear stress has now gone up. We now have increased our ability to move that sediment through the system. So the bars in green are the multi-stage fluvial channel, and then the proposed conditions are just the open flood conveyance only design. So this is an iterative approach, and we have to understand what our sediment is in our system and what shear stresses we need to move the sediment through our system, and how to set our design about that. Now, this is the other design consideration to ask your design professionals, or if you're a design professional yourself, consider this in your flood mitigation designs. First of all, how to design a multi-stage fluvial channel. Well, just go out and look and see what's going on in the river systems. We can go out and map and measure stable channel geometry in areas where the sediment is in balance with its floodwaters. We'll go out and measure the cross-sectional area, what the elevation is at bank fill stage, what the elevation is of the floodplain stage, what is our channel profile going through there. And all of this is really well documented in some federal and state handbooks. This is one from the National Resource Conservation Service, a National Engineering Handbook about how to go out and measure and map these channel dimensions. So that gives us a starting point for designing what elevations our benches are at, how wide the channel needs to be to get our stream in balance with its sediment. The next part is going out and counting rocks. That's one of my favorite things to do. It breaks up the monotony of being behind a computer. You go out and you measure the size of the sediment that's moving through your system. Is it sand? Is it silt? Is it small gravels or larger boulders? Because the size of the sediment is a surrogate for its weight. And the heavier the weight the sediment is, the more shear stress that is needed to push that sediment through your channel. So with an understanding of how much volume of sediment is coming down from what we looked at previously, and now knowing the size of your sediment, now you can start numerically going through your iterations with your HEC-RAS model to design your multi-stage fluvial channel so that it doesn't have sediment deposition. Now your last thing is actually the hydraulics, which is part of what we're doing when it comes to flood mitigation design. We have 2D HEC-RAS models, 1D HEC-RAS models, even some other proprietary software programs that are out there that you can actually model the amount of sediment moving through your system under existing conditions and then also under proposed. So you want to match those so you don't have sediment depositing in your flood-prone areas. There are other models you can use, Excel-based models like this one here, which is the bed load assessment for gravel bed streams, or BAGS for short, which is by the Forest Service. And there's some other models you can use to help calculate to make sure your flood mitigation solution moves your system through. Now, we've talked a little bit about the hydraulics, also the hydrology part too. We saw some examples of where we're reducing peak discharges through detention or removing one flow from one basin to another. We can use the same approach to see what happens when we reduce the flow in our streams and how prone to sediment deposition we may become. So some conclusion and takeaways here is that it's no longer a guess anymore. We actually can make informed decisions about where our flood mitigation solutions can be prone to deposition and perpetual maintenance. So those are the things that need to be incorporated at the beginning when we start claiming flood mitigation benefits using our models. So we should think about incorporating that design process at the beginning. When we do, our flood mitigation strategies become resilient. We have thought about sediment moving through. We don't need to have perpetual maintenance on those strategies anymore. So that saves money. It actually improves confidence in our constituents and our people that live around these areas that we can design something that doesn't need constant maintenance. And it improves the environment and the social well-being of people who live along our stream corridors, because now they can engage with their stream. There may be recreational opportunities. So it really, truly reaches all three aspects of that nature-based solution. So with that, I want to say thank you to several people who have helped put this presentation together. And we have our contact information up there in case you want to reach out. And with that, we'll kind of open it up to questions.
I do not have any yet coming through in the board. Does anybody have any questions they'd like to, or is everybody still in a food coma right now? Last chance, any other questions? All right, everybody's still sleeping from lunch, so,
Does this concept work well with kind of the geography we have down here with like low flow or almost zero flow coastal inundation, kind of like Oso Creek? You know, it's pretty flat all the way from, you know, the landfill all the way till it gets out to Oso Bay. So it's something like this. Are we able to do something like this with that kind of situation?
Yes, and I'll take an analogy up by Houston, different geography, but very similar condition. Upstream of Lake Houston, Lake Houston is created by a very large dam. And in Lake Houston, when the San Jacinto River enters the lake, very flat, very, very flat area, a lot of sediment deposits out through there. So then that has got a lot of people concerned about how much flooding is being worsened by that sediment. And so that sediment management can be designed to push that sediment down even further out of those flood-prone areas by manipulating the channel geometry, even in a very flat area, because right up when you hit the lake, the channel profile is very flat. It can also be incorporated when you have tidal fluxes. That is another really strategic part in estuary design, where we account for where mean high water is and mean low water is, and develop the understanding of velocities and tidal channels in there to make sure that they don't erode underneath those coastal fluxes, and also they don't deposit with silt. So the principles of a multi-stage fluvial channel can be applied almost anywhere, from the headwaters in the Rockies all the way down to the Gulf.
Hi, I have a couple of questions. So you mentioned the strategy about, or the technique about comparing shear stresses. Do you also find reliable the HECRA sediment transport tool to predict erosion or sediment deposition in this type of projects?
Could you repeat the question, just the first part?
If you ever use the sediment transport tool within HECRAS to actually calculate, predicted sediment transport when you do some of those channel improvement projects? Yes.
We had a water intake structure up in the city of Cameron. So, and if you remember back in one of the exhibits, there was a meander, a curve in the river. Their intake structure was located at the apex of the meander, taking in water that they would treat and send to the municipality. The river was actually cutting through the meander of the floodplain in between the two bends. And so what that would lead to an oxbow forming, and then the river would basically bypass their water intake, leaving the city high and dry for their water supply. So we used HECRAS 2D to analyze what the sediment transport would be when they move their facility, their water intake facility, upstream of that avulsion where that river was cutting through. And we looked at that for two reasons. One, we wanted to give the city a little bit of information on if they needed to do perpetual maintenance around their intake structure, because they are now moving it into a different location on the river. So we developed a long-term hydrograph and ran that over time and looked at what the long-term accumulation of sediment along the channel boundary was going to be. And I know also in HECRAS, especially in the 2D model, you can run the B-STEM tool, which is the bank stability, tow, and erosion model. That will help predict some deflections in channel bed form too. Those are add-on extensions that you can run in HECRAS. There's also some proprietary software programs, such as Riverflow 2D. The U.S. Bureau of Reclamation has another one that you can run that has a deformable bed boundary over time. So those models do exist.
All right, thank you. I have one more if there's time. So when it's understood the benefits of the multi-state channel, but do you have a strategy in mind for when the right-of-way is very limited and there is not really enough space to have such a cross-sectional geometry, and where you are forced to have something more like a U-shape or trapezoidal shape geometry?
Yeah, it's a really good question, especially in urban environments where we're really constrained by either drainage easements or by utilities, right-of-ways, buildings, that have you. And that's part of that design challenge where my approach is to give the client a couple different options to say, okay, if we make it tight and narrow, we're gonna have to line this channel with bigger rock or cement. If we make it wider, we're going to have running constraints with this utility or this easement, and give them the information and make those decisions on what kind of channel they want, what kind of maintenance frequency they want to go with. So that's part of that design process of being able to lay out a couple of alternatives and give the client some information to make that decision. Question.
Okay, I have a couple more that came in. What ratio of existing versus proposed shear stress causes the concern for sedimentation?
That's a complicated answer. We'll do a graduate degree course here later on this evening.
The question was smarter than me, so I didn't even know how to say it.
Yeah. So I'm going to give the great legal answer is it depends. It depends on how big your sediment is. Is it silt? Is it fine sands, coarse sands, gravels? Because all of those size classes of sediment require a different shear stress. And so there's the differences between taking the shear stress under proposed conditions down 10%. Is that enough to stop, say, a silt from moving through? Is it enough to stop a gravel from moving through? So it really depends on not only the size of the sediment, but also your hydraulics and how much sediment that's actually coming through. So if your entire watershed upstream, there is no sediment supply, not a big issue because nothing is going to deposit out. So that's also part of that depends answer. Yep.
Yes, the upper Texas coast beaches from Sabine River to Galveston are sediment starved because dams on the Sabine and Neches system, and then the Trinity probably also in Galveston Bay, sediment builds up behind the dams, I understand. Has anybody discussed dredging it and moving it down so that we can restore those beaches naturally the way they were built?
I'm sure someplace over a cold pint of beer, someone has talked about that, but I don't know at the higher levels of planning. But I'll give you an example about my experience in the Pacific Northwest. In the Pacific Northwest, they have endangered salmon that the feds have given a lot of power to salmon conservation and protection. And one of those salmon conservation measures is that dam owners are required to go in, scoop up the sediment from the dam, and go around on the downstream end of the dam and release it for for salmon habitat downstream. And a classic example is the Elwha River on the Olympic Peninsula, ELWA. Dam has been there for 90 years, no longer had a power purpose or anything or any flood control. They removed that dam, and within a year, all the beaches where the Elwha River ran into the Puget Sound replenished. And so there's a lot of science and engineering that support moving sediment from behind those reservoirs and letting it to continue down to replenish estuaries and beaches. So there is a lot of science behind that. And whether people are trying to look at that as a measure to replenish beaches or bring in sand from I'm not sure.
Thank y'all very much.